Hi students, welcome to the session on Ampere Circuital Law. In this class we see what is the use of Ampere Circuital Law, the statement of Ampere Circuital Law and its point and integral form, right? So the main use of Ampere Circuital Law is to find a magnetic field at any point, right? So to find a magnetic field at a point in space, provided if there is a symmetry in the problem. That is very important, right? Otherwise we can use Biot-Savart law itself. So to find magnetic field at a point, provided if there is symmetry in the problem, right, then only we can use Ampere Circuital Law, right? So let us see the statement of the Ampere Circuital Law, right? So Ampere Circuital Law states that the circulation of a magnetic field around a closed path is equal to the current enclosed by that path. You see the statement, I can write a statement in the equation form is simply, you see, the circulation of a magnetic field, right? So H dot dl, it is a magnetic field circulation and closed path, right? So the circulation of a magnetic field, this is magnetic field, B is equal to mu H, we know. The circulation of a circulation, here it is circulation. The circulation of a magnetic field, it is closed path. Around a closed path is equal to the net current enclosed by the path. I enclosed is nothing but current enclosed, right? So by writing the equation we can write the statement directly, or from statement we can write equation. So here we must know that some important point here, the line integral, this line integral doesn't depend on the shape of the path or position of the conductor in the magnetic field. So line integral is, line integral, this integral simply is independent of what you call shape of the path and position of the conductor in the field, right? These two are very, very important point. Shape of the path, right, and the position of the conductor. Position of the conductor in the field, in magnetic field. Okay, so this is very, very important point to be noted. That's all about Ampere Circuital Law. This is an integral form of Ampere Circuital Law because we have integration here. So you see the line integral around the circulation of a magnetic field around a closed path is equal to current enclosed by that path. See here, you see the current is flowing through the conductor and we are choosing one Amperian loop. We will deal about Amperian loop in the next class, and from that we can find whatever be the magnetic field around the conductor. That and all we will deal in the next video. Now we see statement only. So now we got integral form of Ampere Circuital Law, which states that integral H dot dl is equal to I enclosed. I hope you must have seen something similar to this in electrostatics. What is that? Closed integral E dot dl is equal to 0, right? We will see the comparison soon, right? Okay. Now we will see one more point. This H dot dl is equal to I enclosed. I use Stokes theorem to relate this line integral and the surface integral, right? So how can I write this H dot dl by using Stokes theorem? That will be equal to surface integral of del cross H, right, dot ds. That is equal to I enclosed. If you have any doubt in Stokes theorem, refer my video on Stokes theorem. So H dot dl I can write as del cross H dot ds. That is equal to I enclosed, right? I know already about I enclosed. I can write I current flowing through any surface can be written as J dot ds, right? So I can compare these two because it is line and current, but it is very difficult to relate dl and ds. Now that's why I use Stokes theorem to convert into ds. So surface integral. Now we can relate left hand side and right hand side. Del cross h dot ds. That is what h dot dl. Instead of I enclose, I write j dot ds. Now both are surface integral and both are equal, means this del cross h must be equal to j. So that is current density. So del cross h is equal to j. This is what point form of Ampere circuital law or differential form of Ampere circuital law. Point form or differential form. You see here the beautiful concept. Now we can conclude. See, current, right hand side I told always cause, current creates, del cross h is what? Curl of h. Curl of h. H is nothing but our magnetic field. So current create rotating magnetic field. That's what we know that, right? Magnetic field will rotate. That's what Ampere circuital law also states. Current creates rotating magnetic field. What is meant by curl? Curl means rotation. That is rotation of H, rotation of magnetic field. So who is the cause? Current is a cause. It creates rotating magnetic field. That is very important point. So you remember these two equations. What is the integral form of Ampere circuital law? Okay, h dot dl is equal to h dot dl is equal to I enclosed. This is integral form of Ampere circuital law, and del cross h is equal to what? J. Both are same only. This current is current. This is current density. Current create magnetic field, and if you are adding, you will get total magnetic field. That's what this one. So current density creates magnetic field at particular point, because del is talking about point. So current density can create magnetic field at a particular point only, because current density is nothing but current at particular point. Similarly, current can create magnetic field fully. So that's what my current I enclose is integration. Okay, now we can compare this with our electrostatic problem. We know this is E dot dl is equal to 0, del cross E is equal to 0. We know that whenever electrostatic field is, curl of electrostatic field will 0. That means what? It will only diverge. That's one. No, curl of electric field is 0. Right? So what is mean? Curl means rotation. Rotation of electric field is 0. That means what? Electric field will not rotate. That we know already. Electric field will not rotate. What about this? Here, curl of magnetic field is not 0. Curl of magnetic field is J only. Curl of magnetic field is not equal to 0, and it is equal to J, current density. So depending upon J value, it will rotate fast. More current, more rotation. So magnetic field will rotate. Curl is not 0. That is, rotation of magnetic field is not 0. So magnetic field will rotate. That's what we know from our school dates itself, right? So that is very important point. So we hope you have remembered our magnetic field diagram and magnet. So here we see we should have drawn the magnetic field lines like this. It will start from north, right? So, and it is going like this, and it is closed loop. Rotation, it is fully closed. Inside there will be a line. It is curl, rotation, right? So magnetic field will rotate. Electric field will not rotate. We know that electric field will be going spread. It will not rotate. Diverge. It will diverge. It will curl, rotate. Magnetic field will rotate. Electric field will diverge. That is very important point, right? So another thing we have to remember is del cross H is equal to J, del cross E is equal to 0. That means electric field is conservative. Hope you have remember. If you don't know, please refer my video on electric field, right? So this equation I derived and proved why it is conservative. Conservative means the work done is independent of path, whereas magnetic field is not conservative. Very, very important. Magnetic field is not conservative, right? So these things we must know. If you are, please refer my video on electric field, then only you will understand that this del cross E 0. Then you will understand why del cross H is not, because it is some big concept, right? So I hope you understand everything very clearly. If you are having any doubt, please ask me in comment section. I will clarify all your doubts. Thank you.